Okay.
First of all, the main important idea of hall probe is to understand the diagram and the dimensions of the hall probe. For example, if we consider a shape like this, so initial shape is important. So for example, if we are using a simple rectangular block or like any simple square or rectangular shape in 3D form, so this is the dimension of the hall probe. So let's suppose this is the dimension we are going to consider for hall probe.
Okay.
So yes. So right now it gives you some idea related to the 3D diagram. So magnetic field lines are coming from like out of the paper. So when they are coming out of the paper, so you will receive like this. So they are coming from backside and coming out from the front side. So this is like out of the paper. So these are the magnetic field lines moving in this direction.
And what about the current?
Yes, we will also discuss about current. And before that, if we mark dimensions, let's suppose this is the thickness. This is the thickness of the sides of the hall probe, and this is the total length. So these are three different dimensions, right? That we are going to use for hall probe. And the third thing, the current. So let's suppose current is moving, for example, like this. We are using variable resistor to adjust the value of electric current. And then, so this is the whole setup for the hall probe, right? So we know that the positive side is on left hand side. And let's suppose we connect ammeter also. So current is going to travel from positive to negative side. So from left side to right side. Okay.
Okay.
And yes, we can also connect a voltmeter to measure the voltage. So let's suppose if you want to connect the voltmeter, so this is the voltmeter connected to find out the voltage. So this is the setup. right? And in this setup, this side represents area. Okay. So basically what happens now, we have magnetic field, we have electric current also. Electric current is passing from the positive side, and the other side represents the negative charges that are electrons, right? So
Okay.
yes, now practically if we observe, so what happens when current moves into this hole prop or this rectangular shape? So magnetic field
Like,
is coming out of the paper, right?
yeah.
And current is like in horizontal axis, right? In simple words, right to left or left to right. So in simple words, we can say field is out of the paper.
So do we use like, can we use the left-hand rule for this, Fleming's?
Yes, exactly. So current is moving from positive to negative. It means left to right, and magnetic field is out of the paper. And now the third quantity is force. So definitely force will be either vertical upward or downward, right?
Right.
So force will be upward direction or downward direction.
Wait, let me do the whole left-hand rule.
Okay,
Would it be downward?
downward. Okay. So due to magnetic field, force acts in downward direction. Okay, so basically in this whole scenario, we observe that left hand rule applies on this whole prop, and we identified that magnetic field is or the force due to the magnetic field on this conductor is acting in downward direction. Okay, but actually what happens? Let's suppose force is acting in downward direction because of magnetic field, right? But electron, you can see electron is on right hand side, right? So all electrons are going to be deflect in downward direction because electrons are free to move. So electrons deflects in downward direction like this.
Oh, okay, so when the force will be downwards, but like
Yes.
if it's electron, right, would it be upwards instead? Because it's like having a negative. So be not up, I mean not down, it'll go up then.
Yes. So normally if you consider from positive to negative side, it will be downward, right? And electrons will deflect in downward direction, like in the bottom of the Hall prop, right? If we consider current from like right to left, okay? Okay. Okay, so electrons are free to move, so electron deflects in downward direction, right? And
Yes.
continuously, when electrons are continuously deflecting in downward direction, so definitely the quantity of electrons starts to increase in the bottom, right?
Okay.
So electron starts to increase.
Like the number of electrons?
Yes, because electrons are deflecting in downward direction, and it will increase the number of electrons in bottom side. So it will creates like very strong negative charge in the bottom, right?
Yes, okay.
Yes. And definitely when electrons are getting more and more, so it creates like a strong electric field also, right?
Yeah.
So electric field now starts to move in downward direction, because in bottom side we are getting negative charge. So the upper side becomes the positive one.
So then there's like a potential difference created as well.
Yes. So it will create electric field in downward direction from positive to negative side.
Okay.
Yes. So now, if we write some points related to the Hall prop. So first of all, we can say initially electron deflects downward. Second part, the bottom face of the Hall prop. Bottom face of Hall prop becomes negative and so an electric field develops that gets stronger as electron deposit at bottom. And the third point is at a certain point, the electric force will increase as much to cancel out the magnetic force. So basically, now you can understand the concept what is happening. Electrons are moving in downward direction. So we are getting more and more electrons as compared to the initial state, right? And when we are getting more electrons, so it will give you more stronger electric field, right? And when we have greater, stronger electric field, So electric field increases and it becomes equal, or it can cancel out the magnetic field, or like force due to magnetic field, right? Because more and more electrons are moving towards the downward direction. So it will make your electric field stronger, right?
Okay, yes.
And what happens then? No electrons further deflects in downward direction. All electrons now can move easily in the forward direction in a straight line. Okay.
Okay.
So finally, we observe that all electrons can move straight without any deflection like this. Okay. So initially they are deflecting.
Okay.
Yes.
But then later on, like they become again like neutral, like kind of like gamma rays.
Yes. Exactly. They move in a straight line. It means they cancel out electric field, cancel out the effect of magnetic field, and they move in a straight line without any deflection. So it will increases as much to cancel out the magnetic force. So no more electrons will deposit at bottom, and the electric field will increase to a certain maximum value.
So does it just stay at this maximum value? Like, is it constant?
Yes. So basically, this is the voltage at which all electrons are moving in a straight line without any deflection. So that specific voltage at which all electrons moves in a straight line without any deflection, just like we discussed. So that voltage is called Hall's voltage, right?
Okay.
Yes. So the last point, the voltage increases to a maximum value. All electrons starts passing straight through. So this is known as Hall voltage. So this is the concept of the Hall voltage. And for the derivation, or to find out the equation for the Hall voltage, we know that we consider both forces opposite to each other, so they cancel out each other. Again, it means force due to electric field is equals to magnetic force, right? So force due to electric field is equals to the force due to magnetic field. and it will be equals to VQ over D is equals to, so Q and Q cancel out each other. But both V's are not same. One V represents the velocity and the other V represents the voltage, right? Just
Yeah.
like the last time we discussed.
Yeah,
So
I remember this.
yes, so we can change the symbol like this. And further it becomes equals to, or V over D is equals to electric field directly like this.
Okay.
Yes. And if you remember from AS, we studied the concept of that electric current or the number of electrons per unit volume.
Yeah, I equals to A and VQ.
Exactly. So we can use that formula I equals to,
A, which is area, and then N is the number density, I think.
yes,
And V is like the
electric
free
field
drift
average,
velocity and
yes,
charge.
charge. So area can be like we can write area D into T. According to our diagram, this D and T is making up the area, right? Through which we can see.
Yeah.
Basically, it depends upon your diagram. If someone is making diagram in some other dimension, so definitely lengths will be different. But right now in our diagram, D and T are making up the area through which the magnetic fields are passing. So in this equation, we can say I is equals to into Q like this. I is equals to N D into T. And if we again split this value of E like this, V over D. So this V becomes Hall voltage divided by the distance multiplied by same 1 over B into Q. So D and D cancel out each other. And finally, we got equation like this.
Okay, so this is like deriving the.
And now we can shift all the values on the other sides to make Hall voltage as a subject. So VH will be equals to,
It would be equal to I over BI over NTQ.
correct.
Also, isn't I over Q also like equal to um no,
Time.
that's different. Yeah,
That is
like I equal
Q
Q over
upon
T.
T. Right. We can also say that. So, but it depends upon, we can say the question, because right now, we are not working on electricity or current electricity topic. We are working mostly on magnetism and electromagnetism. So if in some question we require, so we can make that change. Otherwise, we use the same idea. So this
Okay.
is the idea of the Hall probe. And again, the important thing, your diagram is important for you. So it depends upon the dimension, that what dimensions we are using to find out the Hall voltage. So it will not remain same every time. Again, it depends upon the diagram. Okay.
Like it could be a circle as well, right?
Yes. Okay. Now, if we consider past papers question from Hall probe and other topics also, because this is the topic that we left in this magnetism section.
Yes.
So let's see the past papers or the topicals question first.
Okay.
Okay, last time we practiced a few questions from the normal concept of charge in a uniform magnetic field. And further, we consider a question. Twenty-two, 21. Okay, so this is the question related to the Hall prop. In the first part, state what is meant by a magnetic field. So simple to explain, right? It is a region in a space around a magnet where another magnet experience or any other magnetic material experiences force of attraction by that magnet, right?
Yeah.
So we need to copy paste the definition. In B part, a rectangular piece of aluminium foil is situated in a uniform magnetic field of flux density B. So you can see now diagram have different points. So it depends upon the diagram. You can see magnetic field is moving now in downward direction and motion of electrons are towards right hand side. So the magnetic field is normal to face PQRS and electron. Each of charge minus Q enter the foil at right angle to the face PQTV, basically left hand side. Next, on figure 9.1, shade the face of the foil on which electrons initially accumulate. So on which face you think initially?
Um, Initially it would be the QTPV, right?
Okay. And if you mark all the points just like we discussed in our diagram, so let's suppose if we mark this area and this one, so this will be the length. This is the area through which the electrons are moving,
Yeah.
and this side becomes positive or negative.
Negative, right?
Okay. And this side will be the distance d.
Because if the electrons initially like they hit that area, so wouldn't that be like initially like negative? I mean positive?
Yes,
I mean,
because electrons are going to be travel on the other side.
Okay.
Yes. And voltmeter in this direction.